Now here in this question it is asked that a p-type semiconductor is, options are positively charged, negatively charged, uncharged, or uncharged at 0 degree Kelvin but charged at higher temperatures. Now such type of question can also be asked for n-type semiconductor. Now to see the concept and to go to the conclusion of this, we have to first see what is the definition of p-type semiconductor. So definition of p-type semiconductor says that p-type semiconductor is a semiconductor that is formed when a trivalent impurity is added to a pure semiconductor. So a trivalent impurity are those elements which have 3 valence electrons, and a pure semiconductor like silicon and germanium are those elements which are having 4 valence electrons, tetravalent elements. So if you add impurity like trivalent to a pure semiconductor, you form p-type semiconductor. And in p-type semiconductor, we have majority charge carriers as holes and minority charge carriers as electrons. Okay, now here in p-type semiconductor we have holes. Holes are considered as positive charge particles in majority, and we have electrons in minority, and electrons are considered as negative charge particles. Now because holes are majority charge carriers in p-type semiconductor, that does not mean that p-type semiconductor is positively charged, because holes are mobile charge carriers. They are not going to decide whether p-type semiconductor is positive charge or negative charge. Okay, now then what type of p-type semiconductor is holding the charge, whether it is positive charge or negative charge, or whether it is electrical neutral. Now to go into this concept, we should know first now what is intrinsic semiconductor. Now intrinsic semiconductor, we have silicon and germanium. Now we will specifically see here silicon. Now if you see a crystalline structure of silicon, it will look like this. Now we know that silicon is having 14 orbiting electrons, out of which 4 are valence electrons, and these valence electrons will form covalent bond with the adjacent atom silicon atoms. Say for example, we are having a silicon atom here. Now it has 4 valence electrons. This is 1 valence electron, this is 2nd valence electron, 3rd valence electron, and 4th valence electron. Okay, now these valence electrons will form covalent bond with the valence electron of adjacent atom. So say for example, this is the adjacent silicon atom. It is having its valence electron here. So this valence electron will form a covalent bond here. Similarly, this valence electron will form a covalent bond here. Similarly, this valence electron will form a covalent bond here. Similarly, this will form a covalent bond here. And this is a crystalline structure now of silicon atoms. Now this is an intrinsic semiconductor. Now every silicon atom here will have 14 electrons, 14 orbiting electrons, and in that silicon atom we will also have 14 protons. Now electrons are negative charge particles and protons are positive charge particles. Therefore, because they both are in same number, the silicon atom is electrically neutral. Okay, now all these silicon atoms which are there in this crystalline structure of intrinsic semiconductor, they are electrically neutral. So as a whole, the intrinsic semiconductor is electrically neutral. Now from this, if we remove the silicon atom at the center and if you add a trivalent impurity such as aluminium, then the structure will look like this. Now here we know that aluminium is a trivalent impurity. It will be having 3 valence electrons. So these 3 valence electrons will make 3 covalent bonds with its adjacent silicon atoms. So here you can see this is one covalent bond, this is another covalent bond, and this is third covalent bond. But in the fourth covalent bond, what will happen is there will be a short of electron because aluminum will be having only 3 valence electron. It doesn't have the fourth one, but silicon are having 4 valence electron. So in this here you can see the electron of aluminum is missing because it is having 3 valence electron, and that vacant place of electron is considered as hole. So here we say that this is presence of hole, and this is the incomplete covalent bond. Okay, now if you add a small amount of impurity like aluminum to silicon, then there will be lot number of such holes produced, and that complete arrangement will be called as p-type semiconductor. Now to see here, we have already shown that intrinsic semiconductor silicon is having 14 orbiting electrons and it is having 14 protons in the nucleus. Therefore, silicon atoms as a whole are electrically neutral. If you speak about aluminium, now aluminium will be having 13 orbiting electrons, and in the nucleus it will be having 13 protons. Now here also the number of electrons is equal to number of protons, so even aluminium is electrically neutral. Now if you add a such impurity like aluminium to pure semiconductor like silicon, both the atoms are electrically neutral. Silicon is also electrically neutral. Now all these atoms in this crystalline structure of silicon atoms are electrically neutral, and even the aluminum atom is electrically neutral. So when you add electrically neutral atoms together, the complete arrangement is also electrically neutral. Therefore, we say that p-type semiconductor, which is formed by adding a trivalent dopants like aluminum to intrinsic semiconductor like silicon, it is electrically neutral because the number of electrons orbiting those particular atoms will be equal to the number of protons in the nucleus. Therefore, as a whole, p-type semiconductor will be electrically neutral. So we can conclude that in a p-type semiconductor, the material as a whole is electrically neutral because the positively charged protons in the atomic nuclei balance the negatively charged electrons in the normal crystal lattice. Therefore, the option that is uncharged, option C, uncharged, that is electrically neutral, is the correct option. Therefore, we conclude that a p-type semiconductor is uncharged. Option C is the right answer.